Okay, so in this video, we're going to talk about regression, regression and correlation. Let's begin with a sample data set. In this case, we have a sample of 1,034 Major League Baseball players. One of the variables measured on each player was their weight in pounds. So we could see here, right, we have a reasonably symmetric symmetric data in terms of its frequency distribution. Recall here that this is the median. This here is the third quartile, and this here is the first quartile. Recall here that this is the this bar here we have is Q3 plus 1.5 times the interquartile range, and that all these dots here are deemed to be outliers. All right. Notice that we have no outliers to the left. So that's just a way of recalling how to read a box plot. We can also, so the box plot was recording their weight, and below we have a histogram that's also recording their weight as well, and it's recording the weight in terms of a density, a percentage density. So here, right, this looks here a little bit strange. It's saying 0.02, but that's really just saying 20%. Right? Oh no, sorry. No, I didn't mean that. That really is just saying 2%. Okay. So there we're numerically summarizing the weights of these players, and we're also presenting a nice histogram as well, where we're comparing, where we're looking at their weight in pounds and looking at what percentage of players, what's the relative frequency of players that have that weight. So, okay. So now, a natural question here to ask would be if there's a relationship between a player's height in inches and their weight. This would be a natural thing to do, and so of course it would be natural to form a graph for, a plot where we're looking at height and weight and looking to see if there's a relationship between the two. Is there a relationship between height and weight? Right. So this here is what's called a scatter plot, because each point, let's say, pick this point here. I'm going to draw this point here in, let's pick, say, this point here. This point here corresponds to a player whose height is roughly 72 inches, and their weight is roughly 240 pounds. Right? So we take all 1,034 players, and for each one of them we construct such a point, and we call this a scatter plot, and we're comparing each player, we're comparing height and weight and seeing if there's some kind of a pattern. Okay. Notice here we have this box here in red, like this one here. This represents this could be players. They all have the same height, and so here we're getting a sense of, the way in which if there's some kind of relationship between height and weight. Notice here too as well there were outliers, so you could think of this box here as maybe being, given a fixed weight, given a fixed height, this would be the distribution of your weight. Okay. So if there is a relationship between height and weight, then one question to ask would be if it's a linear relationship, right? So it's tempting to look at this picture here and maybe draw a line like this, right? That would say, roughly speaking, as the person's, the taller the person, the heavier you would expect them to weigh. And then you would wonder if there is a linear relationship between those things. All right. So if the relationship between two variables is linear, then there is a single number, right, a numerical summary, which summarizes the strength and the direction of that linear relationship. That is what we call correlation. And then a next question we would have is, given one of the variables, for example height, can we build a reliable equation, or what's called a model, that we can use to predict the value of one of the variables using the other? Namely, can we construct an equation to predict the weight of a baseball player who is 72 inches tall? This is what's called a regression model, or, a least squares line. All right. So what have we spoken about so far? We have this notion of bivariate data, for example, height versus weight. Namely, you have data that has two variables involved, and then we have a graphical summary of this bivariate quantitative data. We should have stressed that we're interested in quantitative data as well. And we do that using scatter plots. Okay. So of course, if we measure two variables on each object in a sample, then we have bivariate data. Bi is for two. If both of these variables are quantitative, then we have bivariate quantitative data. We could think of another example where we look at the weight of a car and how much mileage it gets, namely miles per gallon. So we could look here at the population of all cars and draw a sample from it. We would have a sample of 25 cars. The object in question that's being drawn is the car, and for each car we would have its weight and its mileage, right? And so since both weight and mileage are quantitative, it would make sense to have a scatter plot here. Okay. So the question we would be interested in, in this instance, right, is if we're interested in how car weight affects or is related to car mileage, then we would have car weight as being what's called the explanatory variable, because we are using it to explain the car mileage, right, or to predict the car mileage. Right. Similarly, we were using the height of the players to explain or predict their weight. Right, and so in this case we call the height the explanatory variable. The response variable, or the variable that we are trying to predict, is that which we are interested in, right? So, which variable should go on the horizontal axis? Well, the variable that should go on the horizontal axis should always be the explanatory, because we are interested in using that variable to predict the other, to predict the response. Alright. So here's our example of car mileage. So in here we have weight as the explanatory. Right. And mileage is the predicted variable. Okay. So here we're using weight to try and explain what mileage ought to be. You could see that we have a scatter plot that displays each object, and the sample is a point, and the location of a point is determined by the values of the two variables of that object. For example, here, this point here corresponds to a car whose weight is roughly 4,000 pounds, and its gas mileage is 27. So that's where that point comes from. You might notice as well that this looks like, this might be a pretty good line for predicting this, but of course we'd want to make it pretty good, more accurate. But that's the basic idea, right? So in each of these examples we have a notion of direction. So here you could see the direction. As the explanatory variable gets bigger, so does the predicted variable. Another question to ask is, do the points form clusters or groups? Do the points clearly follow the chosen form, or is the relationship not as clear? And also, are there outliers? Are there points that do not fit the overall trend? for example, here it looks like we have, say, this point here does not fit the overall trend here in red. And the rest of the points look pretty good from what I can see. Okay. You could argue here, you might say, oh, this one here doesn't maybe look too good, but then that also depends on what we're using as our predicted blue line as well. All right. Okay. So here's a natural interpretation of the scatter plot. Ever before we try and draw, any kind of line, it seems not entirely surprising that heavier cars have lower miles per gallon. So there's our interpretation. In other words, there is a negative relationship between weight and mileage, right? It also claims, and this is something we're just eyeballing, is that the relationship does appear to be closely linear and there are no obvious outliers. So notice another way of saying that is if we were to use this line here, which we're drawing in blue, that seems like a reasonably good fit, reasonably good regression model or prediction model. And notice that the negative relationship means that as the weight increases, then the miles per gallon appears to decrease. All right. Likewise, in the players' heights versus their weights, it looks like there is a positive relationship between height and weight. The relationship isn't obviously non-linear, so linear seems like a reasonable guess, and there are no obvious outliers either. Okay. So, if you notice that after constructing a scatter plot, that the direction or form is counterintuitive, then double check that 1, you plotted the correct variables, and 2, that you put the explanatory variable on the horizontal axis, right? Or like what you're used to maybe calling the x-axis from your previous classes. Okay. Now, let's get on here to this, how do we summarize the strength and the direction of the linear relationship between two quantitative variables? And we also mentioned this notion of correlation. So let's investigate that next, right? So we have a number, Pearson's correlation, which we usually call R, which I'm highlighting here in red, right? And that is the sample correlation, right? It's a numerical summary of the strength and the direction of the linear relationship. And linear here is very crucial, right? For example, you could have a scatter plot that looks like this, right? You could have a scatter plot that looks like this, right? Right? Clearly, there is some relationship between the two variables here in your scatter plot, right? You could probably easily find an equation that fits that that fits that data very tightly. But what you definitely don't have is that you could say that there is a line that really fits that data. So there's really no such line that fits that data. So what we're about to say is, when we speak of summary, is strength of the strength and the direction of the relationship between the two variables. We're really emphasizing that we're only concerned in cases that are linear, at least for now anyway. So R has certain properties. It's always between -1 and 1. The closer it is to -1 and 1, the better the relationship, right? Or sorry, the stronger the relationship. R being positive means that there is a positive linear relationship. Likewise, if it's a negative, there's a negative linear relationship. R is equal to 0, or close to 0, means that there is none or little of a linear relationship. So in the toy example that we drew over here in the corner, right, we would expect the R to be more or less 0, because there's no real good line, right? So you'd expect it to be very close. Okay. So here we have some nice examples, right? You might wonder, what the relationship here, it's very clearly positive, and you'd expect it to be strong. Here it's very clearly negative, and you'd expect it to be strong. So you'd have R less than 0 here, and you'd probably have R being close to -1. Here you'd have R greater than 0, and you'd expect R to be more or less +1. here, you could see that all these kinds of lines here might be equally as good, right? Or sorry, what we should say is equally as bad. Really, there's very little linear relationship here in this one on top. Okay. So, you know, as already mentioned, a value of r close to 0 indicates no linear relationship, right? Again, don't confuse this with there being no relationship of any kind, right? For example, here's a pretty good curve that indicates a relationship between the two variables of the question, but it's not a line, right? So again, we're only talking about linear relationships, right? Some more properties of R. The size of R in absolute terms indicates how strong the linear relationship is, right? So closer to 0 is weak. Closer to 1 is strong. In fact, if it's equal to 1 or minus 1, then not only is it strong, but it's exact. Okay. So here in this exercise, this is an interesting exercise to match the correlation coefficient with the graphs in question here. So it might be easiest here to pick out this one here first. When the relationship is exact and positive, that's most likely this one here, right? Let's look at another one. We've got two options here that are negative. You could see here this is very close to 1, so it's probably this one here, right? Here you have a negative relationship, not close to 0, but not close to 1 either. It's probably going to be this one here. And finally, you have something that's not close to 1, not close to 0, you know, reasonably good but not great, and it's probably going to be this one here. Okay. Most of the time, we're going to calculate the correlation coefficient. Sorry, we certainly won't calculate it by hand, right? Because it'll be, you know, well, you know, we won't even give the formula for calculating it by hand. That'll come in a later course, what's called the least squares method. Instead, we're just going to identify the correlation in SPSS output, which we'll get to talk about soon. In SPSS output, we have it here, right? So so what we're doing here is that we're comparing weight and mileage, and you can see here that this is the correlation coefficient, right? We could reverse roles, of course, and compare mileage to weight, and notice that you'll get the exact same correlation, right? This is just a way of saying, you know, when you're running SPSS, it's not at all fussy about what your explanatory variable is and what your responsive variable is, right? So it's kind of pumping out. So it's producing both of these correlation coefficients, right? And you could see that that's pretty decent as well, right? Because you could see you're going to get a pretty strong linear relationship here in the original data, right? And as claimed, your correlation is, negative, but also pretty strong. There you go. So that's how to read it from SPSS. You can also read it from your TI-84. You'll see again the instructions on page 57 and on 499, and here you go, right? It'll produce the same correlation code. Okay. Finally, how do we interpret this? How do we interpret this? Okay. Here's what we're going to say. And again, let's just stress. So, of course, we always start off with determining whether it's positive or negative, right? And here's our general rule of thumb. And let's really emphasize this is a rule of thumb, okay? A rule of thumb is that if R is at least 0.8 or, you know, or less than negative 0.8, then we declare the relationship to be strong, right? Although, again, in practice, this will depend on the field of study, right? So in something like deciding the effectiveness of a drug, or a relationship between some, say, for example, some kind of genetic attributes and the chances of you getting cancer, you really have a very high threshold, right? You really want to be certain, right? So this will always ring true, but for now we're just going to say or, exceeds 0.8 or is less than negative 0.8. For that, we're going to consider that to be a strong relationship. So, for example, we say that there is a strong relationship, a strong negative relationship between weight and mileage of a car, right? It's because we got a regression coefficient that was negative, and it was less than negative 0.8. All right. The Major League Baseball players' heights and weights. Here we're seeing we get a regression coefficient of 0.532. We say that this is, excuse me, we say that this is not necessarily strong, but moderately strong. And I know that might be kind of annoying, right? But we're going to say this is moderately strong because it's greater than 0.3, but less than 0.8, right? So we're going to say this is moderately strong. And if we have something that's, less than 0.3, we're going to say that that's weak. Back here a second, I'll just make a note of that, right? As a general rule, we're going to say if the R is between negative 0.3 and positive 0.3, then we say that the relationship, we should really say the linear relationship, we say is weak. All right. We say is weak. All right. So, last slide. You know what? Okay. Last slide. Very, very important. A very common mistake that people make is that they say, "Ooh, I've got good correlation, hence I have a causation." Right. So it's to distinguish between correlation and causation. Right. That always requires a great degree of subtlety. Namely, don't confuse cause and effect from correlation, right? Because often there can be what's called a confounding or a lurking variable. Confounding is maybe, the more common term that we use, right? So here's a really nice example. It's that we've got data from Copenhagen in the 10 to 12 years following World War II. And they noticed something very interesting. They noticed there was a strong positive correlation between the number of storks nesting in the city and the number of babies born in that same year. Right? So what they did was that they got a scatter plot that looked something like this. Right? Scatter plot that looks something like this. Very strong linear relationship. So if you think correlation is the same as causation, you would say, oh, if you want to increase the population in the city, then you just have more storks, in the city, right? But of course, the real reason for this, is as follows, right? So certainly, as you have more people, you're going to have more babies, right? As a general rule, I hope I don't have to explain that to people. And also, if you're going to have more people, then you may also have more storks in the city, because there's going to be more food to scavenge. So the more people you have, the more storks you have. So here you could see that people is your confounding variable, right? Storks are attracted to people. People get together. The more people there are, the more babies there are going to be. And so the real effect is that you certainly have a correlation between between number of babies and number of storks, but it's because you have, a correlation, if not even, a cause and effect, between number of people and babies, and also number of people in the city and the number of storks that would be in the city. Right. Okay, I'll stop there.